All right. Today we're very happy to have Keiichiro Furuya from Northeastern University visit us. And he did his PhD here, and he'll going to be telling us about towards the complete classification of holographic entropy inequality. Please.
Thank you. Thank you for the introduction and thank you for the invitation. So today I'm going to talk about towards complete classification of holographic entropy inequalities, the work with Lim Bao and Joy Lee at Northeastern University. So here in this talk, I have two parts. First is I will talk about the problem that I want to solve, and then second, I will give you the solution. And then for the first part of the problem, I will clarify what really we want to solve. And that was like also an important contribution of this paper. And then for the second part in the solution, we will give the algorithmic solution, but I'm not going to talk about the detailed algorithms, but I'll give you the steps. But I will motivate those algorithmic solutions from these two topics. Okay, so let's start with part one. So main problem, sorry. Okay, yeah. The main problem statement that we wanted to solve is to find all holographic entropy inequalities. So I will describe what it means. What do I mean by this? So first, I will review what the entanglement entropy is, and then I'll review what the holographic entanglement entropy is, and at the end, I'll review what the holographic entropy inequality is, and then we'll motivate why we are interested in this thematic problem. So first, entanglement entropy. So consider a pure quantum state. You can think about a whole system partitioned into A and A bar. And then the density matrix or the density matrix associated to the subregion A can be defined in this way using the partial tracing over degrees of freedom in A bar. And then the entanglement entropy of subsystem A is defined as this one. So this is a quantum mechanical quantity. And yeah, so this is very basic. So this is the building block of our story. So this is true for, you can study entanglement entropy for a quantum system. Now people study a specific quantum system, which is a holographic system. So in holographic system, people found that the quantum information quantity, which is entanglement entropy, corresponds to some geometric object. In this case, a geodesics that anchored on the subregion of the boundary theory. So in short, briefly, the holographic theory has two aspects. You have a boundary theory and you have the bulk theory. And then the basic idea is that the information inside the bulk is encoded on the boundary. So if you extract some of the information on the boundary, even the subsystem, you should recover some of the information inside the bulk. And here I'm taking A as the boundary subregion here. It's a boundary subregion. And then this boundary subregion has the information of this bulk region bounded by this gamma. This is the geodesics connecting these two. And this is called the Ryu-Takayanagi surface. And then the region here, the bulk subregion, bounded by the boundary subregion, and then the RT surface or Ryu-Takayanagi surface is called entanglement wedge of the boundary subregion. So this is the lightning review of what the holographic entropy is. Yeah. Okay. So the key thing that I want you to have in mind is that the information quantity, which is entanglement, is has some geometric object or the bulk dual object in the bulk. Okay. If you guys have any questions, please stop me anytime. Okay. So these are the so holographic entanglement entropy is our building blocks. And then you can compare two different entropy entanglement, holographic entanglement entropies. Or even in quantum system, you can have like this entanglement entropy and then compare them. So first inequality is called the subadditivity. Here you have a subregion A and B, and you have A and B, and you can calculate the entanglement entropy of SA, ST, and SAT. And then you can find that this inequality is true. And then you can also have like three-party system where you have A, B, C. Also, there's a purifier. But in this case, you calculate entanglement entropy of AB, BC, and B and ABC, and then you find that this inequality is also true. An important thing is that these two inequalities are true for quantum system and holographic quantum system. But what's important is that there are some inequalities that quantum system does not satisfy. And then one of the most famous one is the monogamy of the mutual information. And this one has this form, SAB, BC, CA, and ABC, and SABC. And this one looks very similar to strong subadditivity, but surprisingly, if you have a holographic theory, then this inequality does not hold. And then people are curious about like what are the special inequalities that only satisfy the holographic system but not the quantum system. And people found a bunch of inequalities, and then interestingly, this paper found more than 2,000 inequalities, or like 1,800 inequalities by their own protocol. So people are interested in what are the
How do you define holographic? What's the definition?
What's the definition? Okay. What's the definition? Okay, so roughly speaking, it's if your theory, let's say you have a quantum theory, like quantum system, and you have some theory on it. And if that has a bulk duals or like the dual theory onto it, you can say it's a holographic theory, but more precisely, if you have a CFT, so this is like ADS CFT2, this is the one example, but not all the CFT2 has good spacetime as a bulk dual. So some CFT has just a quantum system that's not holographic, and then some CFT has this holographic system. And then the definition for that is that the CFT with a large central charge, and then there's a condition for the spectrum. But yeah.
Actually, maybe the question is a little different. Maybe these inequalities hold for the right-hand side. There are consequences of geometry. So if there are states for which this holds, it must hold for this. The derivation is all based on geometry. Right? Is that
Yeah.
Inequality for entropy, but for the area of those.
Yeah, these are inequalities for the area of the surfaces. Now, if this is true, which we have a proof of, at least in some way like this.
Yeah. Was that the question or?
Well, maybe so it kind of sounds like you're saying holographic system is not a quantum system, or
It's the special type of quantum system.
okay.
Yeah.
But
He said not for what, but he meant not in general.
Right. Not general quantum system. So let's say you have
the special type of quantum system.
Yes,
that has
exactly.
this boundary.
Right. So this is like let's say this, roughly speaking, this is the set of quantum states, like the general quantum states. And then the holographic states is something inside. So what I'm saying is that for first two inequalities, sorry, I'm going back. The first two inequalities, quantum states in here, all of them satisfies that inequality. But the this part of the quantum space does not satisfy the MMI. But
Okay.
the quantum space here satisfies that.
Okay, thanks.
Yeah. And I'm saying that the studying the inequality for this is a specific quantum system, but I'm trying to motivate why we're interested in studying this quantum system with the inequality. Yes.
Question. Can this inequalities be proved in higher dimension? I mean, in all the dimensions, does it work also?
Yeah.
So when you say only holographic quantum states satisfy the MMI?
Yeah.
Are you saying that the only known examples are holographic states? So you're saying it's known that there are no other quantum states apart from the holographic states which satisfy MMI?
Well, there are certain type of quantum states that satisfy the MMI, which I will give you an example. So certain type of, so the quantum state that has a certain entanglement pattern satisfy the MMI, and some does not.
And these certain quantum states don't have to be holographic or
Don't have to be it's a little bit difficult to say, but I would say don't have to be holographic. When I say that, it means that I don't have space-time metric that is dual to the theory you have.
I have a generic question. Suppose so this S is a function of a set.
Yeah.
If somebody gives me a function of a set that satisfies a bunch of inequalities, is there enough properties that I can say this is the entropy of some theory or?
Oh, I see. Oh, yeah, that's actually very, so you're saying that not starting from the given set, not starting from the theory to derive inequality, but let's say you have a set of inequalities and then say that what kind of theory you can get. So this is like highly non-trivial question. For a specific case, you can do many interesting things, but I do not know the general theory. Yeah, but I think it's a very interesting question. Yeah. Okay, so this cyclic inequalities, this is one example, is also a holographic inequality that does not satisfy the general, only the holographic states can satisfy. And then people are studying this holographic entropy inequality a lot in various frameworks. And then recently, there's a very, very interesting work by Vertex finding that the inequality has some topology that you get at the torus, or you can extract some geometry from the inequality to construct some geometric object. And then you can study the properties of inequality on that geometry. Yeah. But I'm not going to talk about it. If you're curious, please check this. Okay, so then why do we care? So I kind of already talked about it, but the entanglement, as I told you, that entanglement is some related to geometric objects. But the thing is, not all the entanglement patterns, as we have seen, not all the entanglement patterns satisfy the inequality. For example, this 4-party GHZ state, this is a quantum state, like qubit, 4 qubits. But this 4 qubit state does not satisfy the MMI. As you can see, if you calculate each term, SAB, BC, CA, all that kind of thing, this is the property of GHZ, but if you take the partial trace of it, the entanglement entropy is always 1. So in this case, if you calculate this inequality, you see the inequality doesn't hold because you have 3 terms here, 4 terms here. So inequality doesn't hold. So in this way, I have a quantum state that by its MMI, but I'm not sure what's the boundary or like the space-time metric. Yeah. So in this way, yeah.
So how do you know that the geometric dual to this is not something other than EDS3?
I mean, well, this first, this is just a 4 qubits. So I think the degrees of freedom is too small. So I'm not sure. Well, it's not the EDS3. Okay, so my answer is I don't know. There might be a way to say that there's a space-time, some exotic space-time that I don't know corresponds to this 4 qubit GHZ. But so that I don't know. But my point is that for a quantum state that has this entanglement pattern, GHZ entanglement pattern, cannot satisfy the MMI. Yeah. So for example, in QFT state, if you have a Z to Z entanglement pattern in that QFT state, then that state should not satisfy the MMI.
So, this ABC, what is the pattern, like, how do you, tripartition or bipartition this particular state?
By the subregion, like the
Yeah.
geometry, so it's actually up to you.
We have this four-party J is the state, right? So S of ABC.
Yeah, so for example, here you can say that this is A, qubit B, C, qubit O, O as a purifier. And then you can do A, B, C, or. And then you take the partial case and calculate the entanglement. Okay. Any other questions? This is actually the end of the introduction. Good. Okay. Yeah, okay, so let me state the main problem statement like in detail. So the main problem statement I said was like find all holographic and entropy inequalities. And then in detail, this is the problem I want to solve. So given m as a positive integer, so m left and the m terms with the unit coefficients of entanglement entropies. So think about the convex composition of entanglement entropies of unit coefficients. And this Li to Lm, you can think of it as a vacant box where you can put the single subregions. So L1 can be AB or ABC or ABCDE, and then you have some other entanglement entropies of composite quantum system. And then Lm also can be like GHI or something like that.
Are they disjoint?
They are disjoint. Yes. Sorry, L1?
Li and Lj, are they disjoint?
No, they don't have to.
They could be over.
They could be, they can overlap.
L1 could be AB, L2 could be BC.
Exactly. Yeah. So yeah. And then so this is the input of the problem, and then what we want to do is to find all possible right-hand side terms. So all possible convex composition with the unit coefficient here, where you have R1 and Rn. So you have n terms with n a positive integer. And again, R's are defined similar to L's. So R1 can be AB and R2 can be BC and can have overlap.
Why unit coefficient?
Very good question. So it's the next one. So you might think that why the unit coefficient? And then, so the thing is, maybe the entanglement entropy can have no unit coefficient, for example, like 2, the C1 can be some coefficient like 2, 3, or like 100, and then you have these inequalities. But the important thing is that the holographic entropy inequalities only have rational coefficients. This is the very important input of this observation. So this has been proved. I'm not going to do the proof, but there's an original paper, this paper, holographic entropy cone. They formulated convex cone out of the entanglement and like the set of entanglement entropies. And then they proved that the set of holographic entropy inequalities form a rational polyhedral cone. And I'm not going to describe this one, but what it means is that all the holographic entropy inequalities are a span, or sorry, all the holographic entropy cone is generated by the finitely many extreme arrays with the rational coefficients.
Finitely or finitely?
Countably infinite. Yes, yeah.
Potentially infinite.
Yeah, yeah.
I think countably infinite.
Countably infinite, sorry. Yeah.
Quick question. If I have like a inequality with rational coefficients, on the right-hand side, for instance, that one, I can divide D1 by square root of 2.
Yeah, but you can always multiply by the denominator, because the definition of rational number is that you can always write it as some integer number over integer number, right? So like you can always write 5 over 6 or something like this. It's a rational number.
Yeah, but what I'm saying is if I can pick up some inequality with irrational coefficients.
Oh, no, that's outside of holographic entropy. So that cannot be the holographic entropy.
No, but I'm just hooking up that up based on what we already have. Suppose that's inequality has integer, sorry, rational coefficients.
Uh-huh.
And the new inequality with irrational coefficients is I divide D1 by square root of 2.
Okay.
Suppose D1 is larger than 0.
Suppose is one is, okay.
Then that's, the right hand side becomes smaller, so it still is an inequality.
Okay.
And it's irrational coefficient.
That's a well, let's see.
It's like a loser inequality, but it is inequality based on your original inequality, right? So
Let's see. Yeah, I'm not sure, but it should be fine. It's just a restating. It's like, but like in this well, I think what you're saying is that you have a rational number system, and then you add the irrational number.
No, I think the same is that all the inequalities we're gonna talk about are tight, meaning that they could be saturated.
Oh,
And the state that's saturated, and that's rational polyhedral cone, means that there is a countably infinite number of extrema. Extremal rays of this cone are countably infinite.
you mean there are probably infinite number of cases that saturate? Is that the extreme?
You could view it that way, yeah,
Yeah.
countably infinite vectors.
I see.
Like, it's not, there won't be a continuous variable worth of saturation.
Oh, okay.
But they're all tight, right? They all could be saturated.
They all could be saturated. They all could be. Sure, yeah.
No, like tensor
I mean,
products. Tensor products.
Yeah, that's fine.
They're all
Yeah,
saturated.
Okay, then the square root of 2 doesn't
Yeah, that
work.
doesn't work.
yeah.
Okay.
Okay, and then, yeah, so once you have the rational coefficients, then you can multiply like with the denominator and then get integer coefficients. And then this is we do this because of the later purpose, but once you have integer coefficients, you expand them into unit coefficients. So basically, the holographic entropy inequality can express as the convex composition of entanglement entropy with unit coefficients.
Sorry, I missed that part.
Yeah.
How? Mr. How did you go to unit coefficient?
Yeah, so let me give you the example. So if you have a, let's say that this is a, let's say you have like very stupid example where like this inequality.
Yeah.
Then what you do is you just expand this. So you have the same.
Oh, there's
entropy,
no
but the same-
condition.
Yeah.
There's no condition on how many times the region is repeated or something.
No,
Yeah.
yeah, no, that's fine, yeah. Yeah, so this L1 or SLR, you can think of it as like a box, so you can put like, and then you have like the balls are the set of disjoint, these like single region, these are the disjoint regions.
Yeah.
So you can put this one in here, in here, in here, something like this
Yeah.
multiple
Yeah.
times. Okay. I mean, if there is a constraint on how many times I can put it in, that would be nice. Because that's one constraint, but we still don't know if there's a good constraint like that, yeah. Yeah. Okay, yeah, so this was the example. So n was the number of terms on the left hand side, and then n is the n plus 1 is the number of disjoint regions, and O is always a purifier. So when I say n equals to 3 something, it's the number of disjoint subregions that can appear in the inequality. And then so for example, when m equals 3, you have 3 terms. But but with this, even if you pick the same n and a small n equals to 3, you can have like A, B, B, C, C, A. This times like you put like A twice, B twice, C twice, but in this case you have like A, B, C single times. But the question is, what are the lower bounds of this one that you can find? Yeah. Yeah. And then one thing I want to mention is that the capital M is what I will call the mathematical parameter, because this controls the number of terms, and it doesn't really tell you about the parameter for the physics, but small n is a physical parameter. It tells you how many subregions that you're going to deal with.
Sorry, just
Yeah.
want to make sure I understand. The example you wrote, there are two SA into SA plus SA.
Yeah,
Can I have SAB plus SAB plus SAB?
yeah,
Oh.
sure, you can do that. Yeah. In that case, you have n equals 2. Like if you only have like A, B, just in there.
And M is 3.
M is 3, yeah.
Okay.
So M, sorry, so maybe the example might not be the best, but M and N can have a different number. Yeah.
If you have qubits, then the small n would be the number of qubits, maybe -1.
It doesn't have to be number of qubits, but you can do it because let's say you have a 10 qubit system, but you can have like n can be still 3 because you can you can have subsystem A for the first 3 qubits, subsystem B for the next 2 qubits, and then C for the next some qubits, something like that.
Okay, so you are given this m, and also you are given the subregion you are allowed to use.
Yeah, exactly, yeah. Yeah, but one thing I want to be very careful, I will stress this later on. But in this problem setup, I didn't mention anything about small n. Yeah, so that's like very important part to make the problem very general. Yeah, but basically, if you want to have a specific inequality, you need to determine m and n both.
So M is the number of terms on the left-hand side?
Yes.
What about the number of terms on the right-hand side?
The capital N.
Capital. N,
Yeah.
I see. So there are 3 counter.
Yeah, exactly. Capital M, the
Capital
number
N,
of terms
capital
on the
N, and
left-hand
little
side.
n.
Capital N for the
Yeah,
right side.
got it.
Thank you. Good. Any other questions?
Is capital N given or?
No, so that's the very important part. So here, input is only the left-hand side term.
I
So, and then the number term here can be vary. So here you have like single term, 3 term, 4 term.
So you're given little n and big n.
Yeah. For a specific problem. Yeah, but in general, we only have capital M as an input of the problem.
If the third one is true, then the first two will also be true again.
Yeah. That's also true. Yeah. But actually, this one is in mine, if you remember a few slides ago. Yeah.
How to check whether any equality holds?
Very good, very good. That's gonna be the next part. Yeah. Very good, thanks. Okay. So we have the inequalities, and then from now on, what we are going to do is that I'm going to reformulate this inequality in the language of graph theory. So I'm going to represent inequality as a graph. So when I say graph, and then I will show you. But once I did that, then I'll restate the problem into the graph theory language, and then we'll show you the solution. Okay, so here,
Just one.
yes.
Is it a priori clear that there won't be any nonlinear inequalities? Because when you say all inequality, yeah, is it clear?
When you say nonlinear, means that the entropy
SA
functional.
squared, SA squared plus SV is larger or equal to something.
Let's see.
Something
Yeah.
like when you say cone,
Yeah.
you're saying
Yeah.
that that's not gonna happen.
Yeah, that's what I wanted to say.
But how to
But
prove that?
prove without using entropy cone.
I mean,
Because entropy cone is a convex cone, which is a linear system. Can you have, I don't think you can have nonlinear inequality generated by the cones.
So you argue for it being a cone for the following reason, that if the state satisfies an inequality,
Yeah,
a bunch of states do, the convex compositions will satisfy the same inequality.
Yes.
Prove that.
yes.
Oh, maybe that's sufficient to say it must always be, yeah.
Yeah, if it tells you that it generates all the inequality, then that's a statement.
That's kind of crazy that you could roll that, but yeah, sure, yeah.
Yeah,
That's beautiful.
okay, yeah. Right, so here, the inequality we have, so at this point, let's, maybe we can forget a little bit about the problem statement and just focus on the, shifting the representation. So here, this is the inequality, we wanted to understand. And then what I will say is that the convex composition of the with the unit coefficients on the left-hand side and right-hand side corresponds to the graph, so-called the partial cube that I will give you the definition soon. And then on the left-hand side, we will have something called a hypercube graph, which is a special case of the partial cube. Okay, and then the inequality relation is represented by what we define graph contraction maps. But so here the two keywords, this is important, contraction and partial cube. And this is something I'm going to describe very carefully. Okay, so let's first start with the object, and then I'll talk about the relation of two objects. Okay, so this is a hypercube graph. D-dimensional hypercube graph is consisted of set of vertices and set of edges. And this is undirected, means that there's no preferred direction between the vertices. So there's no edge saying like, okay, it goes from this vertex or this vertex. It's undirected. So it's like plain and neutral. And unweighted means that each edge is only each edge is not weighted. It's just like one. It's not like weighted 2, 3, or 5 or something. It's over. Weight is always 1. Or yeah, you can think about it. Yeah, unit weighted. And the bipartite graph. Bipartite graph means that you can always find the bipartition of the vertices. And it means that so the graph is bipartite. It doesn't contain the odd cycle. Like odd. So for example, the square is obviously the bipartite graph, but if you have a triangle graph, this is not the bipartite graph.
Oh, sorry, it means that every edge corresponds to has Hamming distance 1.
Exactly. So yeah, this is I was about to tell, but these are the number of vertices and edges, not that important here. But the most important here is that the vertices of the graph, a hypercube graph, is always labeled by 0 and 1. The binary set, the sequence of binary elements of a set. So in this case, if you have a 1D, you have vertex is 0, this vertex is labeled by 1. And this vertex for 2D, you have two bits, one is 0, 1, 1, 1, 0, 0, 1, 0. And then the edge is defined as the Hamming distance or the distance between two digits. If you flip 1, then that's like 1 distance. But you cannot connect 0, 0 and 1, 1 because the distance is 2. Yeah. Okay.
So the dashed line versus solid mean something?
Oh yeah, so basically in general, you don't have these dashed lines, but it tells you that how to construct a higher dimensional hypercube. So the one-dimensional line can be constructed by shifting the one vertex and then connect them. And then the two-dimensional is like you shift this line horizontally and then you make a square. And then to make a 3D hypercube, you push this square into other direction and then you get the square. And then 4-dimensional, same thing, shift, shift, shift. Yeah. Yeah. So this is the hypercube graph. Yeah.
Result attached to the 2D vertex and 2D minus 1.
D, yeah, 2 to the D minus 1 times D edges. So if this is 1, you have a 2 vertices, 1 edge.
In 1D, are you saying that the edge connects 0 and 1?
Yeah, exactly.
And then is the graph still bipartite?
Yes, bipartite, because like this is you can separate these two vertices into two, and it doesn't have any odd cycle. Yeah.
Just to remind, so bipartite, I don't know, means like you can split the vertices into sets and they only connect in between. I mean,
Yeah, exactly,
sets, right?
exactly.
Like they don't connect in between.
Exactly, yeah.
Set, only across the set.
Exactly. Yeah, thanks for the So when I say bipartite, I said that how it characterizes saying that there is no odd cycle, but it means that you can always divide the vertices into 2. This is like 1. This is 1 one set and then this is another set. And then there's no connection between these vertices within one set. When the graph is bipartite, the edge always goes through like this. Okay, so this is the bipartite graph. Okay, so for example, for the square graph, you can separate. So this is 0, 0, 1, 1, 0, 1, 1, 0. So if you have a square graph, it's a bipartite graph because you can separate two vertices, 0, 0, and 1, 1 as a one set, and 0, 1, and 1, 0 as another set. And then there's no connection between these two because having distance is more than one. Yeah. And then there's no odd cycle. Any cycle you take, it's always even cycle, even number of edges. Yeah.
You figure the dotted lines are not edges, but the dashed lines are edges.
Here I have this dotted line just to demonstrate the construction of higher dimensional hypercube from the lower one. But essentially, you don't have any distinction between solid and the dashed lines.
If like you connect all the four vertices in that way, then how is that a bipartite graph?
Yeah. So so this if you look at this graph, you have 0, 0 and connected to 1, 0. Connected to 1, 1, connected to 0, 1.
Oh,
And then if you bipartite the vertices, 0, 0, 1, and 1, 1 as one set, but it's over there.
oh,
And then 0, 1, and 1, 0 as one set. And then there'll be
So is this bipartition, it's non-unique, right?
it's
Silent and unique.
it's when you say non-unique,
Like here, you're doing diagonal,
mhm,
and the complement of the diagonal.
yeah.
As you go to higher dimensional cube, there's like, you could,
But like it's either like even labeled vertices or all the labeled vertices.
oh, this is unique then.
Yeah, in that sense, it's unique.
Oh, okay.
Yeah.
So there, sorry. Yeah, so there's a, what is it called? The graph comes with Z2 transformation.
Uh-huh.
And, what's it called? The flips them. Send them
Speed
back.
or?
No,
Like the black and white checkerboard.
yeah, it could be painted in two sets of colors.
Yeah.
Yeah.
There's a Z2, there's a, forgetting the term. But yeah.
Okay. Yeah, this is a two.
Involution, it has an involution. Involution is an operation,
Uh-huh.
it's a unique operation that's four-sided.
Oh, I see. Oh, yeah, no, exactly. No. Yeah, of course. This has a bipartite. Of course, this has Z2. Yes, yeah,
okay.
thanks. Yeah.
But it's canonically defined, that was the question. It's
Yes,
canonically defined.
for all the hypercube dimension, because
One vertex, you cannot put any of the neighbors.
Yeah.
But the neighbor goes into the other one, and then you have to paint the other.
Yeah.
exactly.
Why the square to one?
Huh?
Why does the evolution square to one?
So the involution swaps the bipartition, top to the bottom,
Yeah,
and then you swap twice.
oh, it's swap, I see.
Yeah.
Yeah.
Got it.
It's a Z2. Yeah. And now the partial cube, so there are a little bit of technical terminologies, but I will give you the intuitive example. So partial cubes are the graph. The graph is a partial cube if a graph is isometrically, this is very important, isometrically embeddable to a d-dimensional hypercube graph. And roughly speaking, isometrically embeddable means that when you embed your graph into hypercube, then the distance between every pair of vertices should be preserved. So I'll give you the example. And then isometric dimension is the dimension of the partial cube. It's a special dimension for the partial cube. There is minimum dimension of the hypercube graph in which G is isometrically embeddable. So this is just a word. So let me give you the picture. So this is the example of the graph G, labeled with 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1. And then this graph has isometric dimension 3. Okay, so let's see like how this can be embeddable to 3D cube, but not 2D square. So this one can be embeddable to 2D square if you ignore the distance of every two pairs. So here, this is 1, 1, 1. So this is 1, 1, 1. That's fine. But the distance between these two is 3. But if you embed it here, the distance is 1. So this embedding is not allowed. This is not isometric embedding. This is a usual embedding. But here, what we want to have is the isometric embedding. So this one can only be embedded to, it's not only, the minimum hypercube that this can be embedded to is 3D cube, which is from here. So that 0, 0, 0 and 1, 1, 1 has distance 3. So this is preserved. And once this can be embedded to 3D, and in the definition of isometric dimension, it says minimum because all the hypercube, like 3D hypercube, is isometrically embeddable to a higher dimensional hypercube, obviously by construction. So that's why we wanted to have the minimum in the definition. Okay, so this is the definition of partial cube, and I said that the hypercube is the special case of the partial cube because it's the isometric dimension matches with whatever the dimension it has. Yeah. So the partial cube is more general concept compared to hypercube. So we just said that the convex composition, I just did the definition of these two objects. So now I'm going to tell you how these two objects are related to two objects in the inequality.
Sorry, all the partial cubes, are they bipartite?
All the yeah, exactly.
There must be, right? 'Cause
Yeah.
It could be embedded.
Yeah, so here I didn't mention the mathematical definition, but the mathematical definition of partial cube is that it can, the graph is isomorphic to the subgraph of hypercube. That's the definition of isomorphic. Yeah. So any subgraph of the hypercube dimension, hypercube graph should be bipartite because hypercube is bipartite. Yeah. Oh, okay. Yeah. So to relate this holographic a convex composition of holographic entanglement entropy, I will talk about the graph model of in holography. So here I'm considering ADS3 CFT2, which is the example of the holographic system. And here I'm having two input. N equals 3, and then small n equals 3. So we have 3 terms, and then 3 disjoint subregions. Yes.
So the inequalities you're going to talk about, are they 2+1 specific or they are generic?
It's a gen. We haven't proven it, but it should be generic.
You believe it's generic, but
It's-
the arguments are for 2+1.
Yeah. And then I'll tell you why. So the answer is that as long as entanglement wedge nesting is correct, this should be true.
And there's no requirement about the geometry of these regions. They
Geometry.
could be arbitrary, they don't have to be ball shaped or anything, it could be arbitrary regions.
Sure.
Wow.
Oh wait, okay, no, that's very important. Okay, if it's elliptic, I'm not sure, I don't want to say that.
suspect you
Yeah.
want to be careful with.
Yeah, so if it's elliptic, there was a problem with the entanglement wedge, nesting, so let's not say.
Okay,
Yeah.
so let's stick with 1+1
Yeah.
boundary.
Yeah. Okay, so here I have a convex composition with a unit coefficient A, B, B, C, C, A. So in this case, here I'm drawing a specific bulk configuration. I'm not saying that this bulk configuration is one-to-one corresponding to this convex composition. This bulk configuration is one instance that gives you this convex composition. Okay. So here I have AB, and if you remember, the holographic entropy and entanglement entropy is proportional to the area, like the area of the RT surface, which is the geodesics anchored to the boundary region. So if you have AB, this is proportional to the geodesics, this red line that has A and B both. Okay, and then BC, this one corresponds to this, and CA. CA now I'm considering them to be in the connected phase. So this and this is RT surface. And then, so the graph that I'm going to define on the constant time slice are defined as follows. So the vertices, of course it's graph, so you have a set of vertices and set of edges. set of vertices are defined on the bulk subregions. So the bulk region here is partitioned by the RT surfaces. So you have a bulk subregion that here that is homologous to A. This part is homologous to B. This part is homologous to C. This part here, like this green one, just this green one is homologous to O. But there is also some part that is inside here that is not trivially homologous to the boundary regions. So in this case, the vertices, so each bulk subregion, you define a vertex, you put the vertex, single vertex here, and then if n is given, and then the convex composition is given, then you can, this set of vertices has two subsets. One is the set of boundary vertices, the other is bulk vertices. And the boundary vertices are the ones that, whose bulk subregion is homologous to the boundary subregion. Okay. Yeah, and then edges are defined in the following way. So if you have two vertices like this, and then the edges are defined only when it crosses RT surface once. So you cannot draw the edges between this vertex and this vertex directly because it crosses the RT surface once.
It's a dual graph.
It's a dual graph, yes. So you can think of it as this is like a hyperplane arrangement on the Poincare disk, and then you can say that this is a dual graph of that hyperplane arrangement. Okay. Yeah, so now this is the definition of the graph. I just give you the definition of the graph, how to construct on the constant time size. And then I'll argue that this is the partial cube. Okay, because if this graph, if this graph is not the partial cube, then we don't need these, like the holograph, we don't have to talk about partial cube anymore. But we will show that we're gonna argue that this is partial cube. So again, the labeling the vertices with the binary set was a defining property of the partial cube. So here we're gonna think about where this binary set comes in. Sorry. So in here, you think about the each AB, BC, CA, and then we're gonna associate bit strings on each bulk subregions. And how to do is to ask the question, is a bulk subregion inside the given entanglement of wedges, which is like AB, BC, CA, or AB, BC, CA. This is the yes, no question. There's nothing like this region inside of this, maybe this entanglement edge at the same time, maybe this entanglement wedge or something. It's not like maybe it's always yes or no. So here we have three terms. So we have a three entanglement, three RT surfaces. So here I list AB, BC, CA. If the region O boundary, if the bulk region, okay, so here. So I will arbitrarily, this is up to your choice. But for the first bit, I will say this corresponds to the first bit has the information of the RT surfaces AB. What I mean by that is that if the bulk subregion is inside of the entanglement wedge, I will put 1. But if it's not, 0. And then you do the same for AB, BC, CA.
Those are conditional entropies.
Those are conditional entropy.
Right.
I mean,
So when you put 0, when you put 1 for AB that has a value of 1 for B, A, for example, that means that it's inside S of A, it's inside AB and also inside A. Right.
Yes.
So that S of AB minus S of A conditional entropy.
Yes. But here I'm not talking about any inequality. It's just a convex composition.
No, I understand.
Yeah. But are you trying to say that this pattern is the same as?
Yes.
I see. So you're saying that,
Okay, maybe, I have to think more about this. It
Yeah.
sounds like conditional entropy, but anyway.
Yeah, okay. So, but this region, for example, let's take this region, this box subregion here is inside of AB, inside of the red line, but it's outside of the blue line, so it's 0, but inside of the green line, so that's 1, 1, 0, 1, and then you do the same. So this means that in each box subregion, that's up to your choice, but 1-to-1 correspond, 1-to-1 correspondence to by bit strings. Yeah. So
This data is canonically associated with dual graph. Given the graph,
mhm.
you have this data canonically associated with dual.
No. I mean, even if you don't talk about the graph, you can still do the same thing, right?
I think it's just, you identify incident structure based on like how you divide it in subregions. Once you, like you give the subregions, then you can always write that. You have this, bulk subregions, entanglement wedges, and you can always write that.
Yeah, of course. I'm just wondering how far away from geometry I can go. But anyway, let's continue.
I see. Okay. Yeah, so so like each box subregion can be characterized as a graph and then the byte bit strings. It means that you can, because like you encoded this box subregion into the vertex, so you can label this vertex as these bit strings. Yeah. So it means that the graph that corresponds to the box configuration is the partial cube. So like if you have a convex composition, then any instance of the graph associated with the constant time size partitioned by the RT surfaces should be the partial cube.
That's what you meant by saying, so it's the entanglement wedge nesting.
Yeah.
It tells you that it's
Exactly.
partial cube.
Exactly.
I see. Okay.
So
Wow.
even in a higher dimensional cube, as long as entanglement wedge nesting holds, then this argument should hold.
Wow.
Yeah.
What do you mean by entanglement nesting?
Okay. So I try to avoid entanglement nesting. But entanglement nesting means that, let's say, you have a region A and region B that is larger than that includes boundaries of region A. Entanglement nesting means that the if A contains if B, I'm gonna use if B contains A, then the entanglement wedge of B, which is this region, should contain entanglement wedge of A. So yeah. So you cannot have something like this. This is not allowed because this goes out.
So the boundary regions have partial order in their inclusion.
Yeah.
And their bulk corresponding regions must respect. The bulk to
Exactly.
boundary to bulk is
Right.
partial order, is order preserved.
Exactly, yeah. Okay, so now we know that each convex composition here corresponds to the partial cube. Okay. And then now I'm gonna discuss that on the left-hand side part, that should be the hypercube graph. Because so we said that the convex composition gives you some partial cube, but we didn't say that this is always a hypercube. Right. So like, why do we want to have the hypercube on the left-hand side, which is related to our problem? But one reason is that I said that this is like this is a convex composition with input n and small n. But I said this is the one instance, but this convex composition can correspond to another bulk configuration. And there will be multiple other bulk configuration. And so that if you want to make a correspondence between this convex composition, then you should have the whole hypercube so that it covers all the bulk configuration. Yeah, so if you have a convex composition like this corresponds to multiple different sort of bulk configuration. Okay. So on the left-hand side, you give the convex composition as an input.
Yeah.
So the convex condition should not pick a specific bulk geometry. It should cover all the bulk geometry corresponding to this.
You're saying that by choosing different choices of A, B, and C,
Yeah.
for the left-hand side, you could generate arbitrary partial cubes inside the hypercube.
Yeah. Yeah. So this is just a example to give you maybe more idea. But this was the example I gave you. But this covers this part of the hypercube. So it was m equals 3. So it's the number of terms. And then the number of terms of the convex composition is the dimension of the hypercube. So so this one corresponds to this part of the subgraph. This is the partial cube. But this one corresponds to this part of the hypercube. Yeah. But yeah. Well, isomorphism. That's isomorphism. Well, you mean like the two graphs, this one and this one? Yeah. Well, I am not sure, because in that case, you need to change the boundary subregion configuration, which is input for your problem. So once you fix the boundary subregions, the RT surfaces are fixed. So if you have a different boundary subregions, maybe.
Yeah, you can move C and A slowly and.
Yeah.
Yeah.
Well, wait, how is?
Are these, I think these turn out, so because the number of vertices are not the same.
Yeah, like. the-
Yeah.
Yeah, I think the left and right are not.
I like. Yeah, like on the second row, the left, the graph on the left hand side is not the same as the graph on the right hand side. Because the number of vertices on.
No, sorry. So okay, sorry, I forgot to tell you things. So this boundary, this is actually like a O. This is the sub region of the O as well. So you identified these three vertices as well, but yeah.
Because the right side are isomorphic.
Okay.
Well,
I guess you care about the color.
yeah, exactly. So this is so without the label, this is graph isomorphic. That's true. But with the labels, this is not the same graph.
So do I also identify the two, on the second case, the two vertices on green?
Sorry.
Do I identify?
Yeah, this one. Yeah, this one.
Wait, this one?
Sorry, this one and this one. But okay, so this is the boundary subregion of A. This is the boundary subregion B. This is C. But
Oh,
these are
that's
the
C.
boundary subregion of O. So it's different on boundary vertices.
I see. So those three is one.
Yeah.
Yeah. Those three are one.
2, 3, 4.
Yeah. Yeah. So right. Okay. And then again, we come back to the main problem is that so here we consider the specific convex composition, but actually, like I said, this L, you can put like different configuration of boundary subregions. So in this case, like for different n, this should if even if the different small n's, it shouldn't have the same number of terms, but like we can have like multiple different. So the graph that corresponding to this one should cover everything.
So yeah, when N and capital M do
Yeah.
not match, little n and capital M do not match, we still would consider the hypercube, the whole thing?
Yeah, still whole thing.
Okay.
I mean that's like because that's one instance. For example, yeah, m equals to 1. Yeah. Yeah.
And then oh, okay, hypercube H capital M. So
Yeah.
the only thing that, the left-hand side, the only thing that I really care about is capital M,
Yeah, exactly.
I think, from the graph perspective.
Yeah. Yeah, well, it's yeah, this just gives you the different boundary condition, but I can so different definition. So I'm saying that if you have a different L1, L2, L3, this then once you give small n, then it will define the, this boundary vertices. Yeah. That's what it is, yeah. Yeah, so here, I said that so there's you want to have a hypercube on the left-hand side, and then you can have some partial cube on the right-hand side. And then, so that was these two convex compositions, and now I'll tell you about inequality relation. So there's things for the graph contractions in graph theory. What you do is that given a graph, you make a partition of the vertex set of vertices. So here I have A to F vertices colored. Then I make a 3 partition of the vertices like this. Okay, and then graph contraction you need to do like 2 processes. First is that you contract these vertices. So EF you contract to 1 vertex. A, B, C, you contract to 1 vertex, and D here is one. If you do that, then there are 2 edges that coming from one vertex to the other vertex like this. So in this case, you remove these edges. So this process is called the graph contractions. And then this process you can apply to any type of graph. Doesn't have to be hypercube or partial cube. Okay. But then graph contraction maps is something we define, is that the graph contractions specifically acting on the hypercube, and then the output should be the partial cube. Because even if you apply the graph contraction on the hypercube, the output does not have to be a partial cube. So the graph contraction map is constraint map. It's a it's a constraint map. Okay. And yeah, does that make sense?
Sorry, I don't quite get that. You're saying
I'm saying that the graph contraction map, graph contraction can act on any graph. But here we are defining something called the graph contraction map. That sounds similar.
Oh, I see. You're saying it's a constrained graph contraction.
Yeah,
That's
constrained
just a
graph
partial
contraction.
cube.
Yeah, exactly. Acting on hypercube, and it should spit out the partial cube. Yeah.
So the word contraction here is like intriguing. Is it Hamming distance non-increasing or something?
Exactly. Yeah, Hamming distance non. So sorry, I forgot to describe second part. So the graph contraction map, it's contraction because the distance is non-increasing. For example, in this example, let's take 0, 0, 1. Where is it? 0, 1, 1. This is mapped to 0, 0, 1, 1. And then the distance to 0, 0 is 2 on the left-hand side, but on the right-hand side, it's also 2. So it's good. But 0, 1, 1 to 1, 0, 0,
Yeah.
it's 1, 2, 3, but it's now 1.
Right.
I assume this contraction process is like right?
Non-unique, yeah. Yeah, many things.
If I understand, so in this, on the left-hand side of the inequality, even this M, you can construct this hypergraph. Right, correct?
Given, so sorry, can you?
Given this capital M parameter, you can build this hypergraph, hypercube. And then you can do like many different ways, like contracting, and you get, what's the name for this?
The partial cube?
Partial cube.
Yeah.
And those automatically satisfy the right-hand side.
Yeah, but yeah, exactly.
Okay.
But the one thing that is important is that this, if you apply just the general graph contraction,
Right.
not the graph
Yeah,
contraction map,
it
doesn't have to be
trying to
partial.
give you this, whatever.
Yeah,
Partial cube.
Yeah. So yeah. So now the relation to the inequality, this is very important. This is is that so now you have a hypercube here. And now the question is whether you have a graph contraction map. So yeah, any question?
Sorry, maybe come back to this at the end or something.
Yeah.
But is there some sort of interpreting this as entanglement with nesting preserving? And because you interpreted this.
Yeah.
Okay,
Yeah. Okay.
Partial graph has to do with
Ah.
with nesting, right? So You want to insist on it so that it's preserving order.
Yeah, right.
Make sense.
So actually, we don't know the answer for that, and I'll come back to you why.
Okay.
So yeah. Yeah, if I forgot, please ask me.
Yeah, for sure.
Okay, so the here, this is the answer to your question initially. So like how do you know that the inequality is holographic entropy inequality? So let's say someone give you, for which we already know this is a true inequality, but let's say someone give you some candidate inequality that you want to verify whether it is a holographic entropy inequality or not. In this case, I gave some example like this. This candidate inequality is the valid holographic entropy inequality if there exists graph contraction map or partial cube on the right hand side satisfying the boundary conditions. So this graph contraction, if there exists graph contraction map acting on the hypercube and gives you some partial cube on the right hand side that respect the boundary condition. So here I'm saying the boundary condition is because I'm giving small n, and then once you give the small n and the inequality, the vertex has so there are like the boundary vertices, and these are fixed for a single region. So this is O, A, B, C, something like that. And then on the right hand side, this should be fixed, and then you need to figure out how to place vertices and edges so that this is a partial cube. So finding the graph contraction maps is non-trivial, basically.
But you said it as if, not and only if. So when you don't say.
Very good,
only
yes.
if, I don't know how you're gonna get all of them.
Yes, very good. I'll come back to it in the next two slides.
By the way, is 10 minutes good?
10 minutes good. Yeah, it should be fine. Okay, maybe I shouldn't say the partial cube here, I can delete it. But what I mean by that is the finding contraction map is equivalent to finding the partial cube. So that's what I say. I mean by like a slash.
Yeah.
But we can ignore this if you want, yeah. Yeah, so this is what I was saying. You have a left-hand side hypercube, which has all the bit strings. And then some bit strings are labeled as A, B, and C, and O. This is defined once you give the composition on the left-hand side. And so on the right-hand side, you fix these vertices, label the vertices. And then the problem is that you need to fill these blank. So this is same as filling the inside of the graph. Okay. So that was kind of intuition. I don't know.
Did you give the numbers on the right side, the existing numbers there?
Oh, so you have a lot of choices, but you need to there is a constraint that the path between every pair of vertices should be non-increasing. So you cannot put 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 here. That's
Yeah,
not
but I
how-
mean, the existing numbers on the right hand side.
Ah.
0, 1, 1, so how do you determine that?
Here, okay, good. So once you give the candidate inequality, then you put, so this is defined kind of like the way you define this table, but this A, B, and B, C, and C, A. If A, this one, this A is inside of A, B, and C, A, so you put 1, 1, and 0. So you pick this bit string for the boundary condition for A, and then B and C and all the same.
Yeah.
And if you look at on the right hand side, you do the same. You have A here, A in here. Oh, I'm sorry, this is wrong.
Be 1.
Yeah, this should be one. Oh, I'm so
But
sorry.
I think in the top should be A, B, C, A, B, C, not A, B.
Yeah, oh, exactly. Oh,
That's
no.
yeah,
Oh.
that's right.
This is terrible typo. I'm so sorry. This is A, B, C, A, B, C.
Okay.
Yeah.
Yeah, that makes more sense.
Then
Okay.
it's 1, 0, 0.
Yeah, that makes more sense.
Okay, I'm so sorry. This is terrible typo. Yeah.
Okay.
Yeah. Good. Right. Okay. So now this answers to your question, the completeness of graph contraction map. So so the completeness of there's things called the contraction map, not the graph contraction map, but the contraction map that's used in holographic entropy form paper to prove inequality. There is one paper previous to ours, written by Min and Joyi. They proved that the contraction map is they prove the completeness of contractual map, meaning that holographic entropy inequality exists if and only if a contractual map exists.
What extra ingredient does it take? Because the if part of it was the graph theoretic statement,
If
right? You said that if you have a hypercube, if you apply a contraction, you get a partial cube.
Yeah.
There corresponds a holographic inequality. That was geometric drawings.
Right.
Now, to say that only if every time you have a holographic inequality, there's such a structure.
Yeah.
How would you go about it?
Yeah, so here, like, you say that the, so this is related to the yes/no question. If the holographic inequality, so, okay, only if is if holographic entropy inequality exists, the contraction map exists. That's what you want to prove,
Yeah.
right? So you take the contrapositive, and then if there does not exist contraction map, there does not exist holographic entropy, and you prove this statement. By yeah,
Yeah, okay, that would do it.
yeah, and yeah. So here we basically translate that proof to the graph theoretical language, and then it's basically the same statement. So basically, so here because like contraction map has a completeness, the graph contraction map also has a completeness. So because of this, if let's say you only have n, but not n like subregion, like small n, but if you have a hypercube m, and then let's say you found the graph contraction that gives you a partial cube.
Yeah.
This is just a graph theoretical statement, but then having this implies that there is inequality or inequalities corresponding to this graph and graph contraction maps. Yeah. Yeah. So the idea is that you already have this table, but the subregion labels are blank. So you can pick the subregion labels to read off the inequality. So again, sorry, this is the type of ABC. But if you take this, if you pick these as a boundary conditions, or these as a choice, then you can read off the inequality by saying that, oh, there's A here in this column, or there's no A here, there's A here, or something like this. So without knowing this, but if you have full table, by putting your choice, so this is a different choice, you can have different
So
inequalities.
you said during the contraction maps, the right hand side,
Yeah.
does it end up, it could end up with a bunch of bulk vertices as well, or do you always get rid of all of them?
You don't always get rid of it. What do you mean by that?
So like, for example, the example of MMI
Yeah.
has SAB, SBC plus.
Yeah, yeah, yeah.
So they have, those correspond to bulk, the point vertices in the bulk.
Sorry, which one?
The left hand side of MMI,
Yeah.
right? There are vertices in the bulk,
Yeah. Oh, this one.
right? There are vertices in the bulk.
Yeah.
Now, when you do the contraction, you're bringing some of the, merging some of,
Yeah,
fusing
exactly.
some of the vertices. Of course, you would like all the guys outside, the boundary vertices, the orange or whatever color that is, to
Yeah.
survive on the right hand side.
Yes.
Well, maybe you want that,
Uh-huh.
but do you get rid of all the bulk vertices, or is it possible that some of them survive? There could
Yeah,
survive,
they
right? There
could
could
survive.
be A, B,
Yeah,
on the
yeah,
right
it's fine. Yeah.
Okay, but you never contract, could you contract the boundary edges, vertices as well? Yeah, I think so.
Boundary vertices?
So
No,
R1 to R capital N, is it possible that you drop one of them?
yeah, sure, you can do that. I think that's fine.
All
As long as
contractions
it's
go.
contraction.
All contractions go, I see.
Yeah.
Wow.
Yeah, so this is the statement that we use, finding all the holographic entropy inequalities is equivalent to finding all, roughly speaking, find all graph contraction maps. Yeah, okay, so now these two are kind of quick. So once we figure out that equivalence, this was the main statement. Given n left hand side, let's find all the right hand side. This can be translated into given certain dimensional hypercube, and then find all the partial cubes coming from this. And then, yeah, and that's the equivalence of two problems. Okay, so once you have this, then you just need to read off the inequality from this graph. So that's mostly all about the my story. And then I'll just tell you there is an algorithmic way. It's not NP complete problem. There is a way to do it, like polynomial time algorithm to do, but like it's still long time. We don't know the optimal algorithm for this, but we kind of know the building blocks of how to do. So basically there are three. First is a partition generator, is that you need to generate all possible partitions of the vertices. And then you do the graph contraction based on the partition like this. And then there is a algorithm called the partial cube identifier, and then you check whether it's a partial cube or not. And if it's the partial cube, then you find the inequality, candidate inequality, like the graph representation.
Is this like a brute force search?
No, actually, if you do, well, you can try to do the brute force, but it's still the polynomial. Now, sorry, when you say search, like which part?
Let's see. Are you just survey over all the possible partitions and then
Yeah.
try them out one by one?
Yeah, exactly.
Okay.
Yeah.
It's a smart brute force search.
Yeah.
It's a brute force search that's done at the level of the graphs, right?
Oh, yeah,
That already has been.
yes,
Yeah.
applied.
Exactly.
but at the level of the graph, it is the brute force search.
Yeah, exactly. Yeah, so like the partition generator, we can use this algorithm called the fast algorithm for generating such partitions. It's actually kind of cool technique, but it's a very old paper before smart. And this one, I already discussed about graph contraction, but this is the second one, partial cube identifier. So basic idea for this is whether the graph is bipartite or not, they check. And then they check some equivalence relation among the edges. I didn't describe, but this has, I think this has some physical significance. It's something I'm thinking still. And yeah, and then the partial cubeness is important because you can say that someone gave you the graph, and then your task is to find whether the graph is partial cube or not. You can actually do this in polynomial time or the quadratic time. But if the graph is not a partial cube, but it's still embeddable to hypercube, but without labels, then it's called the cubical graph or the cubic graph. And find whether the given graph is cubic graph or not is NP complete. So then the problem is we cannot solve the problem. So the partial cubeness is very important. And then this is the example, but after reading off this graph contraction, this is the examples of it, not the all the random ones, but you can read off these inequalities. And then at the end, yeah, so this is the discussion part. So first is like, this is like towards the complete classification. So we don't have a classification yet. So the question is, can we do the classification by classifying partial cubes or any way to classify? We don't know. And actually, like I said, the quantum entropy, quantum states, some quantum states satisfy the holographic inequalities. So we might be able to find some relation to quantum entropy inequalities, the holographic entropy inequalities. And then the physical interpretation of holographic entropy inequality is something very interesting to me. I want to know. So I don't know what's the operational interpretation for MMI, because strong subadditivity has it's called the data processing, so has an operational interpretation, but I don't know about the MMI or the other inequalities. So I would like to know about this. And what's the relation to the geometry, bulk geometry. And at the end, I use the directed and undirected, I use the undirected graph for the holography, but if anyone have idea about using direct graph or like graph theory for other problem, I would be happy to discuss this result. And sorry, the acknowledgement, Liu Bao and Joy Deep. Thank you very much.
Thank you so much. Questions?
Are you here tomorrow?
I will be, tomorrow is Wednesday. I will be here, yes, I'll be here. We can discuss, yeah, but we need to find time because I have other meetings, so.
Yeah, maybe we could speak in the morning, like, I have a meeting at 10, but 9 or 10.
Actually, I have another appointment with Leibniz from 9 a.m.
Okay.
So maybe, and I have another meeting from 10:30, so sometime between. We can discuss.
10 to 10:30.
10 to 10:30.
Any other questions?
Is there a simple and wavy argument for why it's the graph contraction gives you greater or greater sign?
Graph contraction.
Or graph contraction maps?
Oh, okay, so this part I skipped because it was not really necessary for this talk. But actually, because I already have a graph, you can define an entropy on this graph, which is called the cut function. So basically what you do is that, oh, sorry, I don't have a, so basically, yeah, okay, so, oh, I'm sorry. Oh, sorry. Thanks. Oh, okay. Yeah, so once you have this RT surface, you can, so here I define the graph, unweighted graph here, just for our purpose. You can actually, if you really want to define a graph that encodes all the encodes the sufficient information of the bulk geometry to calculate the entanglement entropy, you need to put the weight on the edge, which is like like the RT formula, like gamma A over 4G Newton. And once you define that weighted graph with the actual graph, actual entropy, then you can define a so-called cut function. It's the function acting on the graph that gives you some number. And then if you want to calculate the entanglement entropy of B, in graphical way, the cut function will cut this edge and then calculate how much this edge weighted. Yeah. So you can using that you can so from that you can define the entropy. It's called a discrete entropy on the graph, and then you can calculate the inequality for it, and then you will see the left-hand side term is greater than or equal to the right-hand side term brute force.
I see, so the edge carries weight.
Yeah, exactly.
Okay.
Yeah. Yeah, but when you do the calculation, you'll find that you actually do not need this edge information to prove the inequality. That was like a very important part of the original contraction map. So the original contraction map say that you can forget about the weight on the edge. You can only think about the unweighted wedge and then do all the stuff. Yeah. So computational complexity becomes less because you don't have to calculate entanglement entropy using cut function and all that. Yeah, just bit strings.
Any other questions?
Just to clarify, the reason you believe your results are geometry independent is because of the entanglement, right?
Geometric independence. Wait, sorry, what does that mean?
So the reason you believe the bulk geometry does not affect your inequality result is because you are using entanglement right next to it. Is that correct?
Is bulk? Sorry. When you say bulk geometries, mean like the post bulk space time? Okay. Yeah.
Is there geometric interpretation, or sorry, is there an interpretation to contractions? It's operated algebraically. Is there some sort of conditional expectation?
that's a very good question, and I also want to know. But I think, so. So,
Looks like, this picture looks like a conditional expectation.
yeah, exactly, but, I'm not sure like the domain and range of the conditional expectation here, but. Wait, sorry, so when you say conditional expectation on the like algebra or?
Yeah, in the language of Cassini with, Cassini and those guys, the language of,
Yeah,
large and bit string, whatever, bit threads.
yeah, that's just, yeah,
So you'll be projecting down from A, B, C, algebra of A, B, C to algebra of A, tensor algebra of B, tensor algebra of C.
exactly.
At least this picture suggests that's what you're doing.
Yeah, I see. I actually don't know. The reason is because I don't know I still don't know the constraint from MMI. You can of course do it, for, a strong subadditivity, which is just the monophonicity of the relative modular operator. But in the case of the MMI, it's a little bit, nobody knows, but I really wanted to know.
All right, let's thank Keiichiro again. Thank you.
Yeah, thank you very much.
To arrange the meeting, so.
Yeah.
Are you interested in joining the next one? We're going for dinner. We're thanking Keiichiro for dinner.
Sure, yeah, that would be awesome.
Yeah, sure.
All right.
Yeah, if that's possible.
Yeah.
What time are you?
Just, we're gonna decide, just hang out for a couple of minutes.
Yeah.
Yeah, so I guess from 10 to 10:30.
Yeah, I think that's fine.
I don't know, like if this,